So we have an optimization problem that's a little bit different from the ones we've been doing. The the setup for this problem is we have two cities. We have city of Calverton and Capital City in the places where you see them. So Calverton is up here. In order to travel from Calverton to Capital City, normally we travel on these solid lines. We travel 30 miles south and then make a right turn. Actually, it would be a left turn when you're traveling. We turn to the west on Route 1 and then travel another 50 kilometers to Capital City. Sorry, I should have said 30 kilometers south, followed by 50 kilometers west to Capital City. So there's a proposal to build a new road represented by this dotted line. The question is it's going to be a straight road, but the question is where should it meet Route 1 to minimize travel time? We know a couple of things. We know that the new road is going to have a 60 kilometer per hour speed limit and Route 1 has a 110 kilometer per hour speed limit. So the idea is that if it might be the case that just building a straight diagonal line from Calverton all the way to Capital City makes the distance smaller, but you can't travel as fast on the new road, which means that you may get some benefit by having this dotted line join Capital City earlier so that you can then benefit from the higher speed limit on Route 1. What we want to do is figure out where we should have this new road meet Route 1. In other words, what should the value of x be, such that that we minimize the travel time, given what we know about the speed limits. So the let's see. First thing we want to do is answer the question: what is the quantity to be optimized? That's not the right pen. There's the right pen. And the answer is the quantity to be optimized is travel time. We're certainly not looking for the most travel time, we're looking for the least travel time, but that's a form of optimization. So what we want to do is we want to write travel time as a function of some other variable. Really, it's the only other variable is x. We can see that the only choice that we're making is how big to make that. The only choice we're making is how long to make that segment. In other words, this is the part of Route 1 that's being bypassed by building a diagonal line. So the question is how long to make that. So we want to write travel time as a function of x. This is the way we're going to do that. Let's observe that this is a right triangle. And so the dotted line is the hypotenuse of a right triangle. And its length is the square root of 30 squared plus x squared. So the distance we're going to travel on the new road is given by this expression. And the distance that we're going to travel here, normally we'd travel 50 kilometers, but if the new road meets at a distance of x from its starting point, then that means that we cut off an amount of x and we're only traveling 50 minus x on the new road. So let's figure out travel time. We're going to be able to write it as a function of x is going to be equal to the distance traveled on the new road divided by the speed limit. You can sort of figure out why that is, just using units, by the way. If I want to know what time is going to be equal to distance over, well, let's actually do it in kilometers. It's going to be equal to kilometers over kilometers per hour, because that's going to give us kilometers times hours over kilometers, which equals hours. So that would give us the right units. If we take the total distance and divide by the speed limit on that road, that'll give us the time that it takes to travel the road. Another way to do it is recall that distance is equal to rate times time, so time is equal to distance over rate. So these are just a couple of thoughts on how you reason out how to turn a distance and a speed limit into an amount of time. So here what we have is we have square root of 30 squared plus x squared over 60, because that's how fast you can travel on the new road. And then we're going to add to that 50 minus x over 110, because you're going to travel on Route 1 a distance of 50 minus x and at a speed of 110 kilometers per hour. Now let's find the domain of t of x. We now have the expression for t of x. So what is its domain? Sort of you can read that off the geometry of the problem. I can put x anywhere from here to here. So in other words, at a position of 0 along Route 1 up to all the way at a position of 50. Don't know which one is going to turn out to be best or somewhere in between, but we can certainly define that the domain is 0, 50. And this is kind of nice because now we're back to a closed and bounded interval. We can run the simpler optimization procedure on this problem. So we're going to go through the optimization procedure. We're going to optimize t of x on the domain 0, 50. So t of x is, we already know what t of x is because it's written there. So let me get to writing what t prime of x is. T prime of x is going to equal 1 over 60, because I've got the division by 60, times the derivative of square root of 30 squared plus x squared is going to be 1 over 2 times the square root of 30 squared plus x squared. Because we know how to take the derivative of a square root function. It's 1 over 2 times the square root of that thing. But don't forget that by the chain rule, we have to take the derivative of what's inside the square root, which is going to be just 2x. And then, let's see. Just a second. So the derivative of, the derivative of 50, the derivative of 50 minus x is just negative 1. So I've got minus, well, let me just put it this way, plus negative 1 times 1 over 110. So we'll clean this up a little bit. And this is going to be x over 60 square root of x squared, of 30 squared plus x squared, and then minus 1 over 110. So what we want to do now is we wanted to solve the equation t prime of x equals 0. So that's going to be 0 when these two things are equal. So we want to set, since we're subtracting one from the other, so we want to set x over 60 square root of 30 squared plus x squared is equal to 1 over 110. That's going to give us t prime is 0. So that gives us 110x. I'm just cross multiplying because I have two fractions. So that's 110x equals 60 square root of 30 squared plus x squared. And let's see. So let's divide by 10. That gives us 11x is equal to 6 square root of 30 squared plus x squared. I want to get rid of the square root so I can solve, so I'm going to square both sides. 11 squared is 121, so it's 121x squared is equal to 36 30 squared plus x squared. So once I simplify this, 30 squared is 900. I'll spare you all the multiplication. Let's just come up here, and once I've multiplied everything by 36 and squared the 30, I'm going to get 85x squared is equal to 32,400. So that gives us x is going to be equal to plus or minus the square root of 32,400 over 85. And of course we know that we're not interested in negative solutions of x because we're certainly not interested in putting x way back there, where it's going to be just a positive number. We've already determined the feasible domain of x is 0 to 50, which is all positive. So that comes out to approximately 19 point, I'm just going to cross out the negative solution. So that becomes approximately equal to positive 19.52. So what I want to do now is I'm going to calculate t at the endpoints and at the critical point. This is the critical point. So t equals 1952, t of 50. I've calculated what happens when you take this objective function, which is kind of complicated. I don't want to do the algebra all in front of you, but I've calculated what these come out to. T of 0 comes out to 0.95, and these are in hours, by the way. T of 19.52 comes out to 0.87 hours, and T of 50 comes out to 0.97 hours. So it's kind of interesting what happens here. We can see that if we just basically don't build the road at all and just have people head south and then west again, it's going to take night. Well, actually, it would be a new road because we don't know what the speed limit on the old road is. So we build a new road, let's say parallel to that. It's going to take them 0.95 hours. On the other hand, we just build a straight diagonal line from Calverton to Capital City. It'll take them 0.97 hours. If instead we have the roads meet at 19.57 kilometers, then it's going to be 0.87 hours. So that's the minimum. So just to answer the question, the answer is build the road to meet Route 1, 19.57 kilometers along the way toward Capital City. So that's the answer. So we want this green segment here to be 19.57 kilometers long.